Our atmosphere is just full of teeny tiny particles, way smaller than a light wave, and when light hits them, it gets scattered all over the place. Okay, here's the play-by-play. Sunlight comes screaming into our atmosphere. It immediately starts crashing into billions of tiny gas molecules. Now, and this is the key part, those molecules are just the right size to be a real problem for the short wavelengths, like blue and violet. They get bounced and scattered in every direction imaginable. But the long wavelengths, the reds and oranges, they just cruise right on by. So when you look up, what you're seeing is a sky just filled with all that scattered blue light.
Okay, but hold on a second. If you're really paying attention, you should be asking this question. Violet has an even shorter wavelength than blue, so shouldn't it scatter even more? Shouldn't the sky be, purple? It's a great question.
And the answer is basically a 1-2 punch. First, the sun just doesn't send out as much violet light to begin with. And second, for the violet light that does make it here, our eyes are just way more sensitive to blue. So you put those two things together and yep, blue wins the contest for the sky, hands down. And get this exact same science explains sunsets. When the sun is way down on the horizon, its light has to travel through a much thicker slice of atmosphere to get to you. By the time that light reaches your eyes, almost all of the blue light has been scattered away, leaving only those long, tough waves of red and orange to make it through. It's the same physics, just a different angle. All right, so scattering? Check. We've got the sky figured out, but what about those crazy, swirling, psychedelic colors you see on a soap bubble or in an oil slick? That's not scattering. This is something else entirely. We need to introduce a new character to our story: interference. So this happens when light hits something incredibly thin, like the wall of a soap bubble. Some of the light bounces right off the front surface, but some of it actually goes through the film and bounces off the back surface. So now you have two separate light waves coming back at your eye, and how they meet up is everything. If those two returning waves are perfectly in sync, if their peaks and valleys line up, they join forces and amplify each other. Boom! You see that color and it's super bright. But if they're out of sync, they completely cancel each other out. Poof! That color just vanishes. And since the bubble's wall is always changing thickness, the colors that get amplified and the colors that get canceled are constantly shifting. That's your swirling rainbow.